Hello, everyone. On behalf of the US, UK, Canadian, and Australian Academies of Engineering, I'm very pleased to welcome you all to this Ideas Forum. My name is Guru Madhavan, and I'm Senior Director of Programs and a Senior Scholar in Systems Engineering at NAE. In the 1960s, the economist Albert Hirschman introduced the idea of the hiding hand. He argued that there's some benefit to ignorance in project planning. Because if we knew the costs and constraints in doing projects upfront, we would initiate very few of them. In other words, taking on projects where we underestimate or even ignore the difficulties can trigger human ingenuity. Hirschman argued that such ingenuity made it possible to realize projects on time and under budget, even in the face of unforeseen difficulties. Unfortunately, we engineers know well that such cases are the exception rather than the rule. Ill-planned large projects generally cost much more and take longer than predicted. The technical challenges aren't insurmountable. We do deal with them, but the contexts and conditions in which large projects are conducted are generally far from ideal. And in our discussions yesterday, we heard with great congruence that the technical challenges are exacerbated by organizational, political, social, and professional forces, and more, unfortunately. Because of such complexity, large projects have inevitable unpredictability. This complexity is also why so many large projects follow what's called the break-fix pattern. A project gets started with great optimism, but without a complete understanding of what's required to make it fully operational. Then uncertainties catch up. And at some point, the project breaks in one way or another, requiring a fix, a redesign, a reorg. Because of resources already invested in the project, a break seldom leads to a project's cancellation, but only prolongs it with more costs. I'll share a quick story. Next slide, please. You're looking at the Bayonne Bridge. Engineered by Otmar Ammann with architect Cass Gilbert, the bridge opened over the Kil Van Kull Strait in November 1931. It was the world's longest through-arch bridge at the time, connecting between New Jersey and Staten Island, New York. The steel crescent, 325 feet tall, 85 feet wide, became an emblem of elegance and economy, though less famous than its twin in Sydney. In the early 2010s, the widening of the Panama Canal created a problem for the Bayonne Bridge. A new generation of post-Panamax mega ships couldn't fit under the Bayonne Bridge's 151-foot vertical clearance. The Port Authority of New York and New Jersey had three options. First, remove the bridge and replace it with a new tunnel at a cost of at least $3 billion or 15 years. Second, they could retain the original arch, but rebuild it with the higher cable-stayed model. Also expensive, and this approach would produce an odd-looking bridge. Next slide, please. The third option was deemed the best, although it was the most complicated. Install a new road deck closer to the arch's apex. It would compromise the bridge's elegance, but create the necessary 215-foot vertical clearance. Raising the roadway on a bridge while keeping it open to traffic was an extraordinary engineering challenge. Someone compared it to conducting open heart surgery on a running patient. Building a bridge within a bridge also required safe staging of transit and crane operations. Plus, the project needed to minimize disruption to residential life and local ecosystem. The price tag for the elevation was $1.3 billion. Adjusted for inflation, it was 6 times higher than the original cost of building the bridge. Comparatively, in the 1930s, Amman had few restrictions. No seismic requirements, no concerns about infringing on residential areas, no environmental reviews. The bridge was delivered months ahead of schedule and under budget. By contrast, in 2009, the impact studies required to raise the roadway involved consultations with over 300 organizations and 50 Native American tribes. The resulting 5,000-page report cost over $2 million to complete. The report revealed that the Kilwan Cove is a possible breeding location for about 6 dozen bird species, including the endangered peregrine falcon. Then, of course, the classic issues of NIMBY, not in my backyard, when people understandably oppose any project that they don't want near the neighborhood. And some have real issues like toxic waste dump, casinos, homeless shelters, you name it. And then there's banana engineering. Build absolutely nothing anywhere near anything, where there's wholesale opposition to any engineering project that's big, from shopping malls, stadiums, golf courses. Next slide, please. The re-engineering of the Bayonne Bridge and the West Coast Main Line, as I discussed yesterday, illustrates something common to all projects involving infrastructure management. Call them the grind challenges. Unlike the grand challenges that transfix communities with big, bold targets that push the frontiers of achievement, grind challenges are the myriad interlocking tasks that keep our highly engineered world functioning. They involve testing, inspection, standards, compliance, quality work, care work, all the nuances of negotiating to move load-bearing bureaucracies. Grind challenges are not defined by their blue sky idealism, but by how well they accommodate the nearly impossible constraints on and in the ground. Next slide, please. The very epitome of the grand challenge, the literal moonshot, was undergirded by so many interlocking grinds. The Apollo program, as you know, required contributions of more than 300,000 people, 2,000 contractors, 200 universities. To support this collaboration, NASA managers adopted systems management techniques with a significant focus on clean room protocols and safety critical maintenance checks, nitty-gritty details, that is. Many of the solutions for the technical problems of rocketry turned out to be largely social and organizational. In other words, reaching what Buzz Aldrin described as the moon's magnificent desolation first required a heroic commitment to mastering the magnificently mundane. Next slide, please. At the same time, the consequences of climate change, including sea level rise, extreme weather, both drought and deluge, and the imperative to decarbonize our economy are forcing huge investments in new infrastructure. As we discussed yesterday, precisely because of social, organizational, budgetary, and professional constraints, systems engineering approaches convey promise in managing megaprojects. Today, we'll build on that base and discuss how we should think about shaping multinational project coordination and collaboratives. We'll closely look at what could be done to move the engineering education and skills development agenda a bit forward, even way forward on these matters. Next slide, please. To get us started, we have the Honorable Donald Winter, who served as the 74th Secretary of the Navy from 2006 to 2009 and is chair of the Council of the National Academy of Engineering. Dr. Winter serves as chair of Australia's Naval Shipbuilding Advisory Board and is also Pentagon's Senior Defense Industry Advisor for Ukraine. He's former professor of engineering practice at the University of Michigan. His business career spanned over 30 years in the aerospace and defense sector. He was president and CEO of TRW Systems, later Northrop Grumman Mission Systems, and earlier program manager for space projects at DARPA. He chaired the National Academy studies on Deepwater Horizon exploration and on the options for implementing safest technologies for offshore oil and gas operations. After his remarks, Dr. Winter will also moderate the first block, and then for the second block, hand it over to Mark Enzer. Hayatun Sulam will close out the forum. Secretary Winter, it's been a pleasure to work with you on mega project matters over the past couple of years, and we're delighted to have you with us. Over to you, Don.
Thank you very much, Guru, and good morning, good afternoon, and good evening to everyone, as is appropriate. Pleased to be able to start out the discussion here this morning with a little bit of a provocation, if you will. Let's see, at a time when we are facing existential challenges from climate change and a new geopolitical axis of China, Russia, and Iran, the limited capabilities of our respective industrial bases have become problematic. From the impact of COVID lockdowns on our supply chains to our inability to produce the weapons needed to support Ukraine and Israel, the lack of resilience in our industrial base is evident. Furthermore, from ostensibly well-planned infrastructure projects, such as the California high-speed rail and London's Crossrail projects, to our joint challenges in building naval vessels from submarines to frigates, we are seeing multi-year delays and multi-billion-dollar overruns. In this regard, I will stipulate that these are examples of the limited capabilities excuse me, of both government and industry. For most infrastructure and national security investments, government is responsible for planning, budgeting, and execution oversight, while detailed design, construction, and delivery are mostly contracted with industrial firms. Each must bring to their roles capabilities commensurate with the project's scope and associated challenges. It is important to note that the requisite capabilities continue to evolve as customer expectations and the required incorporated technologies change massively. The capabilities needed to build over 3,000 Victory and Liberty ships during World War II was quite different from the capabilities required today to build just a few Type 26 frigates. Not too long ago, I would have suggested that the capabilities of our industrial base were defined principally by three factors: human capital, physical resources, and intellectual property. Two additional factors have arguably taken center stage in the last few years, materially impacting the resilience of that industrial base: the vulnerability of industry to disruptions in their supply chains and supporting infrastructure. The vulnerability of the supply chains that support major developmental projects became evident during COVID, when national and regional lockdowns disrupted key sources of supply. The impact of such shutdowns was further amplified within those industries that had pursued 0 days inventory strategies to improve their financial returns. An additional challenge arose with the escalation of the conflict in Ukraine. Sanctions imposed by Western governments have interrupted the supply of critical materials such as the titanium used in the aviation industry, much of which came from Russia prior to 2022. And let us not forget that the burgeoning trade war with the PRC has the potential for creating additional challenges to supply chain resilience, as China has or controls much of the rare earth minerals critical to the implementation of the electric-based infrastructure that we seek. And the potential implications, should Taiwan's microelectronic industry come under PRC control, would extend throughout many industries and could fundamentally impact the economies of all of our countries. We have truly moved into a time when the attribute of assured sources of supply is rarely appropriate. If nothing else, the importance of supply chain management has become evident, although many of these vulnerabilities are beyond the ability of private industry to manage effectively. Industry is also having to accommodate an uncertain supply of basic electric power. The likelihood of blackouts is increasing due to a combination of factors, including rapid increases in demand, closure of coal-fired generators, limitations of our electric grid, and the uncertainties associated with wind and solar power generation. In that regard, I find it interesting to note that the build-out of computer server farms in support of the emergence of artificial intelligence is being paced by the availability of diesel-driven backup generators that have been deemed to be essential elements of such facilities. These vulnerabilities share several common attributes. In particular, they will require the cooperative engagement of industry and government to successfully resolve. The public policy implications are significant, as our governments try to address the evolving global security challenges and the threats of climate change. Investments and regulations have many consequences, both intended and unintended. In a world where policy is driven principally by political considerations rather than what we might recognize as systems engineering, the limitations and potential unintended consequences of regulations and investment programs must be recognized and addressed. And the best sources of the needed perspective and knowledge often lies in industry. All too often, industry remains silent, particularly when it sees near-term financial benefit in such an approach. For example, I do not recall the construction industry pointing out in 2009 that the so-called shovel-ready infrastructure projects to be funded by the American Recovery and Reinvestment Act were few in number and small in scope. For those not familiar with the results, I will simply note that of the nearly $100 billion allocated for transportation and infrastructure, less than 30% was spent on such projects. We must do better in the future. Our ability to develop an environment where the uncertainties of supply and power are minimized will have a decided impact on the overall capabilities of our industrial base. The basic capabilities of industry are the result of a highly intertwined combination of human capital, physical resources, and intellectual property. Human capital consists of a diverse set of individuals with the training, experience, leadership, and work ethic needed to bring the often audacious projects to fruition. But human capital is just a necessary but not sufficient means of providing the needed capabilities. Human capital must be supported by the intellectual property that is key to both the design and production of the desired assets. And yes, that IP is the product of other individuals whose work established the enabling technology bases for the project at hand. Lastly, but not least, are the physical assets, the property, plant, and equipment required for construction, test, and delivery that transform the human capital and intellectual property into useful products. Unfortunately, we often forget the interdependencies of these three classes of assets. We see this demonstrated in situations such as Taiwan Semiconductor Manufacturing Company's $40 billion investment to build a microelectronic chip production facility in Arizona. Not quite a year ago, TSMC was forced to announce that production would be delayed to 2025 due to a shortage of trained personnel. Transferring their IP and training Arizonans to produce 4-nanometer chips is a daunting task, further complicated by the challenges of language and a limited base of skilled workers. One feature in common to these three factors of capabilities is the extended time frame and significant financial investments required to establish them. Furthermore, the investments of people and financial resources must be maintained consistently over long periods of time. It takes many years to develop a chief engineer or a second-level shop supervisor, and it takes just a short while off to disrupt that development. In the shipbuilding industry, a few months break in production invariably results in a material reset of the learning curve. The same is true for both IP and physical assets. IP often takes years to develop and is dependent upon the continuous efforts of key individuals, often supported by a sizable team. The journey from basic to translational research to demonstrated technology takes many years. Similarly, facility development can be a frustratingly long, multi-step process encompassing design, permitting, site development, and installation of equipment, followed by the hiring and training of staff. All this brings to mind two questions. How did we get to this point, and how do we fix the problem? I will stipulate that there is much that I would like to say about the mistakes made by government, academia, and industry that got us where we are today. When I first drafted these remarks, I found it fairly cathartic to enumerate just a few of these mistakes, including several that I must admit participating in. However, in the interest of living within my allocated time and moving on to our panel discussion, I will focus on just a few thoughts regarding a possible path for the future. I will suggest that this future path must recognize the enormity of the task ahead. I personally do not believe that our governments have recognized the scope of a transition away from fossil fuels or of the investments required to secure our nations against a new axis threatening us with new technologies. Alone, either one of these objectives would strain our individual industrial capabilities. Together, they represent an enormous challenge, particularly when one considers the timelines required. I will further note that while the challenges appear daunting, they are likely to be less so if our four countries address the problems together. I recognize that proposing a multinational approach at a time when many have proclaimed the era of globalization to be over may be viewed as swimming against the tide. But this would be different. We would be leveraging the joint capabilities of four countries that share a common heritage, have similar values, and rarely differ on our views of the world outside. Add to that the trust built up over years of Five Eyes cooperation, and it is likely that the risks of supply chain disruptions or political conflicts arising in the future would be limited. I will stipulate that given the extended time frame required to achieve these objectives, we will need to ensure that any cooperative arrangement are able to survive the changes of government that can be expected to occur. I say that mindful of this year's elections in the UK and US, followed by Australian and Canadian elections next year. I will suggest that one example of such an arrangement is the AUKUS agreement, entered into by Australia, the UK, and the US. The agreement is fairly wide, ranging from addressing Australia's critical need to replace their aging Collins-class submarines with nuclear-powered but conventionally armed submarines, to a wide range of technology sharing, addressing future national security challenges. I must say that I was particularly pleased to see this agreement survive the recent change of government in Australia and trust that it will survive any change of government in the US or UK later this year. There is no inherent reason why such agreements should be focused solely on defense cooperation. An agreement, say, on developing small modular reactors could augment AUKUS, but with a focus on civilian electric power production. And noting the existing legal constraints in Australia on nuclear power generation, perhaps an alternate focus on DC microgrids for server farms could be considered. Such efforts could harness the engineering capabilities of our four countries and materially advance the state of the art, addressing our shared infrastructure challenges. I do worry that given the fractious political environment in the US, that developing a consensus within our Congress will be a challenge, let alone getting alignment between all four governments. I do see some hope as the dangers of the current situation become evident. That was the situation that led to the US CHIPS Act, passed in 2022 with bipartisan support, providing funding and policy to reinvigorate microelectronic manufacturing in the US. I also note the recent release of a bicameral and bipartisan congressional guidance for a national maritime strategy just a few weeks ago. Hopefully, once we get past the upcoming elections, we can all find areas like these that represent suitable opportunities for a coordinated effort on behalf of all of our citizens. And I thank you very much for listening to my commentary and provocation here. Right now, however, it is time for us to proceed into our panel discussion. And I am most pleased that we have an exceptional group of panel members who have had diverse experiences with very large multinational projects. And to give you a sense of what they bring to this discussion, I will summarize their backgrounds up front. Eddie Isaacs is from Canada, more specifically Alberta, Canada. He is the former CEO of Alberta Innovates, past president of the Canadian Academy of Engineering, and an advisor to government on energy and the environment. Sarah Pierce comes to us today from Western Australia, where she is leading Australia's mega science project, the Square Kilometre Array, a project that Peter Quinn introduced us to yesterday. For the last 3 years, Sarah's been directing the development of a massive radio telescope array spread out over the Australian outback in conjunction with an international team of scientists. Mitchell comes to us from London, where she serves as the deputy chair of ARUP Group. For those of you not familiar with the organization, it was founded to be both humane and excellent, and is focused on sustainable development worldwide. Devilla has had extensive experience in India, the Middle East, and Africa. Lastly, Charlie Bolden, who I must introduce as Major General Charles Bolden, U.S. Marine Corps, where he was a naval aviator and test pilot, flying everything from A-6s to the space shuttle. His experiences with the shuttle included command of STS-60, the first U.S.-Russian shuttle mission. He was later appointed administrator of NASA by President Obama and oversaw the early days of the transition from the space shuttle to the use of commercial spacecraft. I am most pleased that this distinguished group of engineers have agreed to participate in this panel today and wish to thank them all for their contributions. And now we will hear from Eddie Isaacs. Eddie, over to you.
Well, thank you very much, Don. Going back to March of this year, we held a mega projects forum focused on large engineering projects as they relate to infrastructure to achieve net zero emissions by 2050. The forum was led by our Academy of Engineering with participation of industry leaders, academics, and government officials. I think we only scratched the surface, but there were practical ideas and learnings that can assist us in this forum to potentially launch a collaborative effort between our 4 countries to address gaps and find viable solutions to challenges facing large engineering projects. Getting large engineering projects done is competitive. On the one hand, it is a challenge, as this is a global issue, and there will inevitably be some degree of competition for scarce resources in many different forms. On the other hand, it is an opportunity for collaboration and leveraging synergies in working towards shared objectives. The feedback during the workshop was that Canada can't be a selective partner, but needs to be a holistic partner. This was reinforced by a letter to our Prime Minister received last month from 23 US senators bemoaning the fact that Canada is failing to meet its obligations in defense spending to the detriment of the NATO alliance. This is in fact a point that our chair, Don Winter, justifiably and forcibly made during the workshop. Naturally, a greater focus on investment in the military has consequential impacts on key elements of the system, such as labor availability, supply chain, access to technology, and funding for non-military large engineering projects. Nevertheless, engineering to support our military will be important in the decades to come. Some key themes that emerge that could potentially help us work together to overcome our respective challenges include improving on large engineering project delivery. In Canada, we've had cost overruns by 2 to 3 times their original estimates and many-year delays in several mega projects, from hydropower plants to nuclear refurbishments, to pipelines, to oil sands expansions, to urban light rail systems. I suspect that the cost overruns and delays applies to all our countries. Can we work together on providing guidelines on best practice, including how to conduct independent reviews of large engineering projects throughout their full cycle to better control budgets and delays? That's a question. Canada's policy and regulatory system is complex and lacks clarity and predictability, which delays the advancement of projects at the scale and pace required. We believe there is a need for a more visible engineering voice to contribute to ongoing work in this area. Can we work collaboratively to develop guiding principles from an engineering perspective on policy and regulatory advice to our respective governments? So that's a second question. All 4 countries aspire to be at net zero by 2050. In Canada, we lack a shared vision and supporting rigor in a strategy and a plan to achieve our goals. Recognizing that each country does their own analysis, can we still work together and challenge each other by identifying gaps in our respective climate change plans so that we can assist or advise our countries in developing comprehensive roadmaps for achieving our respective climate change goals? Thank you.
Thank you very much, Eddie. Really appreciate those comments. What I'd like to do now is to ask Sarah to give your thoughts, and then we will continue on in the conversation.
Thanks very much. So I'd like to start by acknowledging the Whadjuk Noongar people as the traditional custodians of the land and waters here in Perth, where I'm dialing in from in Western Australia. And I pay my respects to their elders, past and present. I also acknowledge the Wurundjeri Yamaji people as the traditional owners and native title holders of Inyarimana, Ilgari Bundara, the CSIRO Murchison Radio Astronomy Observatory, where we're building the SKLO telescope. And I also acknowledge any First Nations people here today. So I'm a telescope director for the SK Observatory, as introduced, and we are in fact a collaboration of 16 countries, including Australia, the UK, and Canada. In fact, particular congratulations to Canada, who announced yesterday that they have become a full member of the SKA. I'm also on the board of the Giant Magellan Telescope, a US-led mega science project to deliver one of the world's largest optical telescopes. So I'm deeply involved with all 4 countries represented here and really pleased to have the opportunity to listen and contribute to such an expert forum. So many of you will have heard about astronomy yesterday from Peter Quinn, who spoke about the challenges of effective project management of large-scale science infrastructure. I'm going to focus on a slightly different question. So how to establish long-term multilateral partnerships that can deliver mega science and engineering projects. But when keeping in mind John Armitt's question yesterday, I will start by answering the question that John posed, which is why? So with radio telescopes, we can observe the invisible universe. The radio light isn't hindered by gas or dust in space or by our atmosphere. And we can look back in time into the history of the universe as far as the cosmic dawn, when the very first stars and galaxies formed a few 100 million years after the Big Bang. But in order to achieve these science goals, we need to build radio telescopes on a scale never before seen. So in fact, we're building not 1, but 2 of the world's largest telescopes. SKA Low is the low frequency array, 130,000 antennas that look like 2-meter tall Christmas trees spread across 74 kilometers of the outback in the Murchison region in Western Australia. And then in South Africa, SKA mid-frequency telescope with 197 dishes spread across more than 150 kilometers of the Karoo. And this is the world's biggest data science project that will produce 700 petabytes of data every year to be stored and distributed around the world. With this scale of telescope comes a similar scale of international collaboration. The telescopes will cost around 2 billion euros over their first 10 years of construction and operations. There aren't many countries willing to individually invest in this scale of science infrastructure. So as Peter mentioned yesterday, radio astronomy is moving on from its earlier days when countries like Australia were able to build world-class instruments alone. Like the particle physics community before us, our next generation of infrastructure requires multilateral collaboration. So the SKA Observatory is an intergovernmental treaty organization, as Peter talked about yesterday, like the UN or CERN. This is only, in fact, the second time that governments around the world have set up this kind of organization for astronomy, bringing together nations from 5 continents under a single entity. I was part of the treaty negotiations for SKA, and I want to talk about 3 key aspects that were required to bring this multilateral collaboration to fruition. Firstly, how to bring governments to the negotiating table for a project of this scale. SKA was driven by the science community, with the first proposals for the project presented at international astronomy conferences in the late 1990s. But it took 20 years of lobbying to bring those 16 countries around the table. So the first key for a successful multinational mega science engineering project is true stakeholder buy-in and supportive national communities with a compelling vision. The second key is understanding the different drivers for countries in the project. Of course, the science communities from each country are driven by world-class astronomy, but industrial and economic return is a critical part of any government's case for joining. In SKA, this is embodied in the concept of fair work return. So each of the member countries is guaranteed that a share of their contributions will return to the country in industrial contracts. So Canada is building the high-speed digital processing for SK Mid, and the UK leading delivery for much of the telescope's software, as well as hosting the headquarters. And then the third key part of this negotiation is recognizing the individual constraints for each country, whether this is a need to deliver components in kind so that funding doesn't leave the country, or government requirements around intellectual property, or indeed the need to obtain the consent of the First Nations people on whose land the telescopes are being built. Of course, this multilateral approach brings its own challenges. Firstly, allocating the work to each of the countries, ensuring that the expertise distributed around the world is aligned with the priorities of the governments involved. And as Peter noted, this results typically in more interfaces and more and smaller contracts than would be ideal for a standard infrastructure project. So for us, this requires really strong systems engineering, including prototypes at each of the telescope sites and integration facilities to make sure that the systems as a whole are ready. In fact, only a bit over a week ago, we successfully turned on the first small part of SKA Low, the first 500 antennas. And then, like all the other infrastructure projects discussed here, we have to deal with the impacts of COVID and the war in Ukraine and the effects on inflation and supply chains. And to deal with these issues, we need to negotiate with all 16 member countries. And the in-kind delivery that I mentioned earlier can also be challenging. For us, 25% of the telescope construction will be in-kind, with the key here being a full understanding upfront of the transfer of risk between the parties. But overall, it's now 30 years nearly since we first proposed this next generation of radio telescopes. We are now a global collaboration of 16 countries, bringing together more than 1,000 engineers and scientists from 270 institutions. Construction is well underway on both sites, and the telescopes will be operating by the end of the decade. Yes, this model is complex and it takes time, but the multilateral approach mitigates many of the political risks of single country projects, and it allows us to draw on global capability. And what we get is a long-term commitment from governments around the world, buy into the 50-year vision of the SKA Treaty, for which the current telescopes are only the first step. Thanks.
Thank you very much, Sarah. Appreciate that. Some very interesting comments and a very different perspective. And right now, I'm going to hand it over to Davila over in London and ask for your perception of the situation. Davila, over to you.
Good morning, good afternoon, good evening. I'm delighted to be speaking to you here today because I love a major program. However, I'm rather daunted by the scale of what Sarah has just described although I hope you'll find some similarities in my work. My first significant project was Portcullis House in Westminster. At only 200 million plus, it was not only major, but a project in the public eye in a very prominent and historic part of London, which brought about extra pressure. I still say today that this is the most technical project I've ever done, but much of what I learned at that scale has enabled me to move on to mega projects in the billions. And now I can say I'm a veteran of 3 significant airport developments, namely T5 at Heathrow, which was largely UK, but involving international specialisms and contractors. T2 in Dublin, very much an Ireland-UK axis, but with international involvement also. And finally, Abu Dhabi Midfield Pier Terminal, which was a totally international team with leadership moving from the US to the UK, with 30 offices involved from the west coast of the US through to Sydney. And therefore, both time zones and different working weeks did present challenges. I would say that was not an ideal situation because it was not planned from the outset. You could say that the brief was similar for all of these in that the scale of the terminal buildings is close, but every project and every program is different and each have their own characteristics, which mean they need some bespoke thinking, even if some of the principles are the same. Today, I'd like to cover the need and value of collaboration, although we've heard much of that. 2 prerequisites to success, which I think Don talked about a few minutes ago as well. But what do I believe are the success factors? Then my airport examples in a little bit more detail, their characteristics, and then some couple of pitfalls and what I believe are the keys to success. We have heard about the need for collaboration, and I think there are many issues affecting our planet and humankind. And often these are too big and too complex to be solved by one organization. Donald described that well earlier. Local, national, and international collaboration will be required. And with different organizations, whether they be public or private, working together, we can move forward with greater pace, bringing research, innovation, insights, and best practice to bear on these challenging problems. To be successful, we need to bring together the right partners with relevant knowledge and expertise and enable their collaboration with the best tools and technology to understand the issues first of all, and then develop long-term sustainable solutions. The value to the ultimate client is that it enables the best skills to be brought together from the different organizations in different locations. It allows organizations to be more efficient by not needing to develop the same skills in many locations. And the balance of global and local skills is frequently attractive to the client. For the individuals, it provides a development opportunity to work in different countries, experience different approaches, and through this, develop and grow. The advent of digital tools, hybrid and remote working also makes things easier today than it was a few years ago. However, collaboration is not easy, and it's certainly not easy to carry out successfully. And the first prerequisite for success is having a common goal and all agreeing they will work in support of that goal, regardless of different locations, cultures, and norms, etc. Academic literature suggests there are 2 key barriers to success. First, different mandates and motivations of the organizations involved. For example, academia might take a long-term outlook, government might take a more medium outlook, and industry tends towards shorter-term outlooks and delivering year on year to their shareholders. These different outlooks could disable alignment and requires each party to reconcile their differences and their drivers to focus on the common goal. The second one, which I think has been covered quite a lot already yesterday and today, is a lack of resources. And that lack of expertise at the right moment, or the overall lack of resource or lack of funding, can stall or derail a project. It can also lead to inefficient working or not achieving an optimum solution. When we in Arup do a little bit of research on the gaps that are frequently displayed on major programs, we find following things: a lack of systems of thinking, inadequate financial and commercial management skills, poor communications and ability to influence, poor or inappropriate risk allocation, and a failure of change management. There are many factors which might disable good collaboration, but I want to focus quickly on what we can do to enable good behaviours and successful collaboration. The first, as I've mentioned already, is having that common ambition, as it's essential to align a team in each organisation and address their different mandates. Ideally, this is a unique purpose which motivates and engages all parties, and which can be maintained over the long term. Having a project charter is a useful way to achieve this. All parties must feel they have mutual success in the plan and are able to deliver for their own organisations. This takes time to work through with foresight and planning. Today, we cannot deliver just a new piece of infrastructure. We also need to think about the outcomes for the ultimate owner, the users, and the communities. And these can be as broad as creating a sense of place, or more specific, such as efficient operations, job creation, health, or increased biodiversity. But the broader they are, I think, the better. The absolute key to collaboration is achieving strong and trusting partnerships, and therefore from the outset of the projects, it's important to invest time in finding the right partners. Too often, a tender delivers the best cost, but not the best fit. Of course, none of this happens without good stakeholder management and frequent and open communication. I want to touch quickly on some of these projects. Terminal 5 Heathrow, it was part of an ongoing development. The client was a well-experienced client, had in-house team in place, had the supply chain in place, had frameworks in place, and therefore were off to a good start. The project was ultimately delivered on time, no claims, and all matters settled within a short time of the completion of the project. Dublin, on the other hand, was a one-off project driven by a government imperative. Small organisation, inexperienced. Although it had excellent decision-making in place and structured stakeholder management, they were delivered much later than planned because they were driven from outside the project rather than the internals. And the contract closed contractually over many, many years because it was all about the cost. And Abu Dhabi was a one-off project with no experience of scale, and the focus was on a new terminal, not on the ultimate efficient operations of that building. The client organisation seemed large, but governance was unclear. They were inexperienced at this scale, and although they brought in support, the decision-making was obscure. Lump sum contracts drove the wrong behaviour. Abu Dhabi was delivered many, many years later than planned. And the cash flow was so poor for all parties that was very dispiriting. So I think the pitfalls are thinking money is the most important, and a lack of cultural fit, poor communications, a lack of expectations, particularly globally around standards, codes, and qualities when you're working across boundaries. And the keys to success are having a common goal, focus on the broader outcomes, having trusted relationship and partnership compatibility, mutual success, joint working in an environment where people are unafraid to challenge, and open and frequent communications with planned stakeholder management. I will leave it at that so we have some time for dialogue. Thank you.
Oh, thank you, Dorilla. A very interesting perspective. I appreciate your joining us today and providing your comments. And now over to Charlie. Charlie, I see you've got your uniform on, a new uniform. I'll ask you for your comments.
No, thank you very much, Don, and thanks very much to all of you joining today and to my fellow panel members. This has been a great 2 days, and I look forward to the next session also. I want to talk today about the challenge of developing a commercial crew and cargo system to replace the space shuttle system that we began in 2011. At 3:22 p.m. Eastern Daylight Time on May 30th, 2020, the SpaceX Crew Dragon 206 Endeavour on a Falcon 9 rocket roared off the pad at the Kennedy Space Center's Launch Complex 39A, carrying the first NASA crew, Doug Hurley and Bob Behnken, on a commercial spacecraft. NASA's first operational step in commercial human spaceflight had finally been taken, and thankfully it achieved a safe splashdown at 2:48 p.m. on August 2nd, 2020. It's nonetheless important to understand that even with that first successful mission now in the history books, we are still a very long way from having the necessary design, development, test, and evaluation to declare success with commercial crew, as we await the first successful launch of the Boeing CST-100 Starliner, hopefully tomorrow morning, to give us the desired redundancy in our U.S. commercial fleet. The successful launch of a SpaceX Crew Dragon was decades in coming, much longer than most of us realize, and it was not an easy journey. Having been a part of NASA during much of the process, I'd like to share some of my perspectives on the incredible and historic achievements to date. To better inform myself of all the work that went into getting to this point, I went back to a group of NASA executives with whom I had the privilege to work during my almost 8 years as administrator. Collectively referred to as the technical authorities, they were the Chief Health and Medical Officer, Chief Engineer, Chief of Safety and Mission Assurance. The people in these positions were responsible to me for the technical requirements applied to all our programs throughout their life cycles. A couple of decades before the first NASA request for information was released for a commercially sourced cargo resupply vehicle, President Ronald Reagan signed the Commercial Space Act of 1984, stating that one of the objectives of his administration would be the encouragement of the private sector in commercial space endeavors. This enthusiasm for commercial space development was cut short on January 28, 1986, when the nation and the space world suffered the tragic loss of the Space Shuttle Challenger and her 7-member crew just 73 seconds after liftoff. When NASA returned the shuttles to flight in 1988, the movement for a viable commercial space transportation market picked up once again, only to be tragically interrupted by the loss of the Space Shuttle Columbia and her 7-member crew just 16 minutes from her scheduled touchdown at the Kennedy Space Center's shuttle landing facility on February 1st, 2003. After the loss of Columbia, President George W. Bush issued the Vision for Space Exploration, calling for NASA to terminate the Space Shuttle program after completion of assembly of the International Space Station, or ISS, then projected for 2010. Pursue opportunities for the international and commercial sectors to support U.S. space exploration goals, and provide transportation and other services supporting the ISS and exploration missions beyond low Earth orbit. From the beginning, NASA's greatest challenge to commercial spaceflight was the fiscal battle between presidential administrations and the Congress. This became my nemesis and primary focus as administrator. The Bush 43 administration enjoyed much more success than was possible with the administration of President Barack Obama. My belief is that this was due to the Bush administration's interest in commercial cargo transportation, while allowing NASA to remain focused on NASA-owned and operated crew transportation to LEO and beyond with the Constellation program. At the termination of the Constellation program at the beginning of the Obama administration, we saw workforce layoffs of about 6,000 people at the Kennedy Space Center and in excess of 2,000 at Johnson Space Center and Marshall Space Flight Center, and more importantly, a feeling of threat to legacy contractors like Boeing and Lockheed Martin. After termination of the Constellation program, we turned in earnest to the development of a commercial crew program. We established a detailed 2-year review process of long-standing NASA regulations and standards, such as the human rating standards and engineering specifications and regulations. This allowed all interested commercial companies to negotiate with NASA engineers and health and medical professionals on new standards and regulations that would take the best of both worlds, NASA government and private industry, to create the design, manufacturing, and operating guidelines for vehicles and systems that NASA would use to transport crew members and non-NASA astronauts to LEO and beyond. Perhaps the greatest challenge for NASA in putting together this government industry team was to educate the private sector on the critical demands of keeping crew members alive and well-functioning during spaceflight. As crew health and medical officer at the time, Rich Williams wrote to me, "From a health and medical standpoint, challenges have been particularly difficult. Engineering programs are driven by requirements, which are in turn driven by evidence-based standards. This is true regardless of the discipline involved. Health and medical programmatic requirements are driven by standards that are derived from biologic and health-related data. Engineering disciplines all have much in common regarding underlying evidence, testing processes, and analytic tools. Health and medical disciplines are based on an entirely different branch of science, with biologic variability as a key challenging component. Health and medical culture are also very different from engineering culture. Credibly translating and applying health and medical standards and requirements to the setting of engineering programs has always been challenging. In the setting of commercial company cultures mingling with traditional NASA culture in pursuit of human spaceflight, the health and medical requirements were particularly challenging and vexing at some points to all involved. One of the critically important things to understand about the Commercial Crew Program is that it owes much of its success to the Commercial Orbital Transportation Services, later called the Commercial Resupply System, and the lessons learned in its development. Former Associate Administrator for Human Exploration and Operations Mission Directorate Bill Gerstenmaier has gone even farther, opining that our work on the ISS program enabled both the commercial cargo and crew programs to be successful. As might be expected, we had to overcome some arrogance on the part of NASA and contractor teams. It took time and was difficult, but we were fortunate to have strong leadership among all the players with patience to let the teams work through points of potential conflict. Work on commercial cargo was essential as it allowed for a lot of technical and organizational learning in a rapid turnaround, slightly less high-stakes environment. In the ISS program, NASA was required to accept alternate design standards. Pressure vessels requirements are different in Europe, Japan, Canada, and Russia. Structural design practices and electrical standards are different. Even manufacturing and build processes were different. We had to decide how to allow the European Automated Transfer Vehicle and the Japanese Transfer Vehicle to approach the International Space Station captured by the Canadian arm for cargo delivery. We were essentially developing the rendezvous and docking procedures that would later be used in commercial cargo and crew. This all forced our teams to become open to other ways of building space hardware, and it allowed our engineers to expand their thinking as they realized that other approaches to safe crew flights were possible. The flight techniques developed for these foreign vehicles were applied to commercial cargo and crew and minimized the flight testing needed for commercial crew. Also important in progressing to commercial crew and the success of our Demo 2 flight was the fact that commercial cargo wasn't considered essential to the ISS. A failure would be acceptable as long as another cargo mission could be flown in time to maintain the logistics inventory to the station. Since the only real requirement was not to hit the station, higher risk could be taken, allowing developers more freedom to innovate and make rapid changes. We had informed Congress and the public continuously that we should expect failures in the cargo program and that it would be critical for the success of the program that we not be subjected to long independent reviews and extensive delays in the program after an accident. As we had warned, we suffered the loss of 3 cargo vessels over a 6-month period: the Orbital Antares with Cygnus in October 2014, Russian Progress in April of 2015, and SpaceX CRS-7 Dragon, June 2015. Congress, the Obama administration, and the American public all gave us the understanding and leeway we had requested, and we were able to recover from each accident and get each vehicle back into operation as thorough investigations and corrective action took place. Much could be written about the standoff between the Obama administration and Congress on funding for the Commercial Crew Program. In the interest of time and space, suffice it to say that it took 6 fiscal budget cycles, fiscal year 2011 to fiscal year 2016, before NASA's Commercial Crew budget request was fully funded. As a result, the hoped-for availability of U.S. commercial crew capability as early as 2014 slipped to 2020, and we are still years away from demonstrating the business viability of commercial crew space transportation. I will close with a sentiment that I expressed as NASA administrator. And I quote, "The commercial space industry will be an engine of 21st century American economic growth and will help us carry out even more ambitious deep space exploration missions. America's best days in space exploration are ahead of us, thanks to the grit and determination of those in government and in the private sector who dare to dream big dreams and have the skills to turn them into reality," unquote. Thank you very much.
Thank you, Charlie. Appreciate that comment. Very unique perspective. Let me see if Melissa can get us all the panel up on screen. We'll do the panel discussion now. We've got Charlie, Sarah. See, can we get the rest of the panel up? Eddie and Davila also, please.
I need somebody centrally to open up my video. I can't start myself. Thank you.
Okay. Oh, there you are, Davila. And Eddie is last person, I think. He is. We're getting Eddie up here. Let me just start out with a question for Charlie and Sarah, if you will. Both of you talked about the very long period of development, the time that it took from the inception of a concept to delivery. And you talked to the issues associated with, I'll call them political policy matters and the shifts there. You didn't comment much on the changes in technology that occurred over those time periods. And I wonder what you thought was the appropriate mechanism of planning with such great uncertainties associated with the direction of technology. And Davila, I've got a follow-up for you as it relates to the technology used in the planning and development of detailed designs for such massive projects as well. But Charlie, let me start off with you if I could, please.
Yeah, and I'm going to feed into Sarah actually because I'm going to talk about a telescope. But I will say there was not a lot of new technology development with the transition to commercial space for cargo and crew, because in order to save funds, what we tried to do was capitalize on the existing systems. For example, shuttle main engines are now a very heavily modified style, but that's what carries the space launch systems to space. The Orion crew spacecraft, and also the orbital, what we call the service module that the Europeans build. We shipped the orbital maneuvering system engine that was used in shuttle to the Europeans to install in the service module, rather than have them design and build a new one. But the technological challenge that I was going to mention is the James Webb Space Telescope. Massively over cost and massively over scheduled, but it's because people didn't understand. Before we built the first piece of hardware, we had spent $2 billion on designing new technologies. For example, the backplane to hold the actuators for the 18, I think it's 18, is that right, Sarah? 16 or 18 individual mirrors that had to have a coefficient of expansion or contraction, whichever the right technical term is, of 0. In other words, going into almost absolute zero temperatures, 1.5 million kilometers from Earth, we couldn't have them contract and expand. Otherwise, we'd have never been able to tune the Hubble, the James Webb Space Telescope. So $2 billion up front before you build the first piece of hardware. Nobody expected that.
Thank you. Sarah, do you want to add on here?
Yes, so for SKA, I think there were two key things I'd like to talk about here. So the first is the role of precursor telescopes. So in both Australia and South Africa, we have telescopes built by the individual countries, which are great telescopes of their own right, but also test out the technology and the site for the SKA telescopes. And those were really critical for us in being able to do that sort of early technology development. But the other thing I would say is that actually for us, the real key technology is on the digital side rather than on the radio frequency side. And so it's the high-speed digital signal processing and the supercomputing where much of our challenge really lies. And I mean, a key challenge there was persuading the engineers that they should stop moving forward and picking up the next high-speed digital signal processing chip every year as we design, and that we had to stop the design and decide what we were building and then move on towards that. Now with supercomputing, of course, we will buy the supercomputer as close to when we need it as we can. And so I think for us, really, the technology development is more on the digital side and can be possibly more easily dealt with than on the RF side out in the field.
See if I can keep this unmuted for a moment. Talking about the changes in digital technology, Davila, you talked about the software environments that are used for the design of these massive projects and the need to be able to do that across a very large organization, which may be located in different countries. One of the things that I keep on worrying about are the changes in those software environments, those design environments, and how do you keep everybody coordinated in that? I'm mindful of some issues that arose a number of years ago at Airbus when different parts of Airbus were using the same CATIA environment, but different versions of it. And the result was some significant mismatch when they attempted to integrate their first major aircraft. Do you have some lessons learned here that you might offer us in terms of how to work such challenges?
I think the challenge you've identified is a significant one because often the number of parties involved in these major programs from different disciplines needing different software is quite hard to reconcile. I think interoperability has improved a lot over the duration of all those projects which I have described. But the one that was most successful was the T5 project, which the work I'm describing was in the early 2000s, where the client owned the single digital model and set up all the protocols and required us all to work within that, which allowed for automatic clash detection and coordination across all the different disciplines. In the later projects, it was the team that initiated the coordination on Dublin, but in Abu Dhabi, it was, might I describe it as the Wild West. And therefore, there was a really great difficulty in doing that coordination. So I think that it should be something that is set up from the outset of the project. And the benefits to doing that are that the team all know the software they're working with, but the client also, their ownership of the model and their ownership of the data at the end is the most useful thing they have for ultimate operation and asset management. So if we think long-term about this, it's what the client needs. And if they own it and deliver it, that's the most important thing they can do. Can I come back to the earlier question? When we were designing the airport,
Please.
We didn't know, we knew new large aircraft were coming, the NGLAs, the A380s were coming, but we had no idea of their shape, their configuration. And we had to little bit by little bit gain the information from the airlines to help us build that design into our building. So I think this is a common thing we face. We eventually figured out they were 90-meter spans, so we knew what the stands should be. And the next important thing was what was their threshold level so we could arrange the gates. But the information came slowly to us as the aircraft were developed. So I think there's an important thing on these major projects, being able to accept data and information into the project in a staged way and building in flexibility and adaptability into your core design or into the basic design to enable that change to happen. Because if clients can't take advantage of that future technology and a step change in their business, they won't deliver these things that are fit for 20 or 30 years into the future. So I think it's very important to keep that option, those options open.
In that regard, can I ask, did you find proprietary considerations to be a major inhibitor in that type of interchange of information?
On the T5 program, we had agreed to cooperate and we had a behavioral contract, and that enabled us to work closely together. And I think tendering on cost and procurement solely on cost becomes a barrier and an inhibitor to that ultimate sharing of information. So I think if one wants people to share across a very international arena, you have to think about that very carefully and enable the procurement, the systems, the design management, everything to accommodate that.
That's very interesting. Eddie, it seems to me that there are many different small companies that are trying to provide their unique solution to the environmental challenges. Following on to Davila's comments here regarding some of the exchange of information and the need to get a future view of what might be in the offing, can you give us a little bit of a Alberta, Canada perspective on how one gets access to and an understanding of what might be available in the future? You need to unmute there, Eddie.
Sorry. I think technological changes are happening at a very fast pace, driven by things like climate change, the need for environmental sustainability and other issues. And in Alberta, these are taken very seriously, and many of the processes that are being considered are very definitely being practiced. The Alberta government and the Canadian government have been very much focused on technologies that would reduce, mitigate emissions, as well as adapting to climate change. And a lot of money has been spent on these types of technologies. So I think that there are things that are happening. You mentioned small projects. You mentioned things like small modular reactors. I think these kinds of things are taking shape in a way that I think will ensure that we have a better future. Whether they will solve all the problems, I don't think so. But in many ways, they will at least further the environmental sustainability that's required in some of these issues, to address some of these issues.
Thank you, Eddie. One other thing I'd like to just touch on. Sarah, you started your presentation with the Australian acknowledgement to the Aboriginal people. And I know, Eddie, you've also dealt with First Nation up in Canada. I'd appreciate getting both of your perspectives on what it means to be able to work with and get the buy-in, if you will, of the Indigenous people in your two countries. I think it's becoming an increasingly important aspect as we deal with some of the environmental challenges that we're facing today. Sarah, I'll start with you if you could.
Yeah, thanks, Don. So we're lucky in that Australia has quite a well-defined legal framework for engaging with native title holders, so the traditional owners of the lands that we're building on. So there was a 6-year process of negotiation with the Wodjiri Yamaji, who are the traditional owners for the SKA lands. So that negotiation was between the Australian government, CSIRO, the National Science Agency, and the Wodjiri. And that gives the Wodjiri the opportunity to talk about what's important to them. And one of the key things for them is protection of their cultural heritage. So before we start building the telescope, all areas that we're going to build on were walked over by Wodjiri people looking for cultural heritage that might be in that area. And in fact, at one point, we rotated the telescope entirely in order to avoid an area that was of particular cultural significance to them. So we really do see this as a kind of long-term partnership. I also mentioned the name at the beginning of my presentation of the site, which is Inyarimana Ilgari Bundara. So this was a name given to us, given to the site by the Wodjiri, and it means sharing sky and stars. And I think it's a really beautiful demonstration of how we go together forward in partnership, hopefully demonstrating best practice of working with First Nations people.
Don, may I throw something in here? You know, we have my son has been sponsoring a couple of I guess I would call them gatherings, where we bring people in from around the world to talk about space and space related issues. And the very first time we met, we had a Native American who attended, and he was a tribal, I will call him a priest. And he had a great interest in astronomy, but from a different perspective. And you know, they view the moon as a sacred space. And so they wanted to support our efforts to go back to the moon and explore, but they wanted us to do it responsibly. And to hear him make his presentation was kind of eye-opening, when you realize that, you know, the vast majority of the people on the planet are not like us. And we need to listen to them as we do all these technological things.
Well, thank you, Charlie. That's an interesting perspective. I was not aware of that activity, and good to hear from you. Eddie, you want to give us a perspective from Canada and dealing with the First Nation? And please unmute yourself there. Unmute, Eddie.
So I think Sarah described it very well. As to what's happening in Australia is also very much happening in Canada. You know, let's leave aside the historical treatment of Aboriginal or Indigenous people in Canada, which is frankly quite an embarrassment, and focus on what's happening today, which is, I would say that no resource project is going to be built in Canada, or any large engineering project, without the involvement and partnership, Sarah mentioned that, partnership with Indigenous people. So I think progress has been made. It's been slow. There is still a long way to go. For instance, some reservations still do not have clean water. They have to import bottled water, and that's an embarrassment, another embarrassment that needs to be rectified. But I think that as we move forward, partnership with Indigenous people is happening. I should also mention that there are at least 2 bands that I'm aware of, that I've been involved with, that are totally self-reliant and carry on business in a very, very systematic way, and are frankly very rich in terms of financing and being able to take care of their bands. And it's really quite refreshing to see that generations after generations of these bands have been, you know, doing very well.
Yes, thank you, Eddie. Let's see. Develop a question for you. You've had some very wide-ranging experiences geographically, different areas of the world. Guru, when he was talking about the Bayonne Bridge, talked about some of the challenges that were faced from a regulatory point of view, the permitting process that occurs before one is able to start a major development like that. Any lessons learned from dealing across multiple countries in terms of how to address the complexities of the permitting process?
I'm unmuted. Am I okay? I think it is a very difficult area, but I think normally the client is situated in a particular location, and the regulations and permitting that applies are clear. I think one of the challenges we faced on the last project I talked about in Abu Dhabi was that over the course of many, many years, the regulations changed. And there were times when we had to retrofit the building design to meet the later regulations. So I think the danger is much more in the timescales. The other danger or issue I see is that when you have an international team working across many different geographies, they're not always familiar with the requirements of that jurisdiction. And so there has to be, that's why I like the balance of local and global, because you can bring innovation and different experience from away from that geography into that geography, but you can never really do it successfully unless you have that really local understanding of the requirements. And it's that marrying of the two that I think brings around the ultimate success.
Okay. Anyone else like to chime in on that particular question? If not, I've been advised that we're pretty much through our time window here. And I do want to take the opportunity once more to thank our distinguished panelists for such great comments and insights this morning, afternoon, and evening, as the case is in your different locations. And hope that you're able to continue to participate in the rest of today's activities and in the follow-up that I expect will be going on in the near future. With that, I think it's time for me to hand over the conference to Mark Ensler, who's going to run the next panel session on guiding engineering education and skills development. Mark, over to you.
Thank you, Donald. That was the most amazing session. Thank you very much. I found it really inspiring, actually. So as I welcome everyone to Block 4, I just want to kind of notice how amazing and encouraging, challenging and inspiring the last sessions have been over a couple of days. And I kind of reflect on it and think that if I weren't an engineer already, this really would make me want to be one. Because it's exciting. But this kind of brings us round to think that none of this great stuff will happen unless we have the engineers to do it. We kind of need to be developing the engineering skills and capability and capacity. So that's what this block is about. I think an absolutely essential block for us to be considering. It's on guiding engineering education and skills development. And we have a panel of outstanding engineers and educators to help us through this. And so I'll introduce them just very, very briefly, but then ask them to give a better introduction to themselves when they give their opening thoughts. We have Asad Madni, who is the distinguished adjunct professor and distinguished scientist in electrical and computer engineering at the University of California in Los Angeles. We have Jane McMaster, who is the Global Engineering Integrity Director at Babcock International. We've got Yarka Glassi, a professor at Newcastle University, and Kevin Hall, President and Vice Chancellor at the University of Victoria. So an amazing panel. And what we'll do is go to each of them. They will share their opening thoughts. But then, as in the last session, we'll carve out some time to have a conversation which I think will probably flow quite well, but we can go anywhere we want in this area. And I guess the kind of things which will be interesting will be to know how we do attract young people in, how we update existing engineers, because so much is changing so quickly. And also, how can we work with and bring others along to help others who are not engineers understand what we can bring to them, but also how we can plug into other skill sets that are kind of needed for these huge mega projects that we're talking about. So with that very brief introduction, what I would like to do is ask Asad to come on screen, introduce yourself, and share your opening thoughts. Thank you.
Thank you very much, Mark. And hello, ladies and gentlemen. I have an advantage of looking at the topic we're discussing from both perspectives, industry as well as academia. I spent about 40 years of my life in industry, and primarily was geared to developing large-scale systems such as the pointing system of the Hubble Space Telescope, and at the same time, reducing or miniaturizing large systems like gyroscopes and navigation systems into MEMS technology at a fraction of the cost. During that time, there were several revelations that I developed in terms of the skill sets that were needed and the challenges, not only that I faced, but I think that are going to be monumental as we go forward. If we look at today's rapidly changing environment, driven by unprecedented advancements in technology, it is quite apparent that Fortune 500 companies need data storytellers, individuals that understand data science and machine learning at the algorithmic level and can translate, process, and visualize that data into actionable, explainable, strategic insights. The former is being taught at a plethora of universities, boot camps, executive education modules, and MOOCs. The latter, however, is a highly scarce skill in supply. Upskilling is a critical challenge companies are facing across several industries. Many companies like Guild Education and Degreed have stepped into this space to incrementally fill this gap successfully. The challenge, however, is that companies don't know exactly what skills they need or are unable to react quickly enough to rapidly changing market trends in determining talent needs, making these short course bootcamp style solutions suboptimal. This is where universities must fill the void to adopt what I would call subscription models for their alumni who can re-engage with knowledge periodically throughout their lives and become exposed to the latest technology trends, basic skills in those trends, and systems thinking to decipher the implications of those trends. The K-12 STEM education pipeline is currently bifurcated by solution type. Necessary changes to what I call in the classroom curriculum, connectivity, and infrastructure to effectively teach engineering and science principles are perceived as political. While creative, novel, and technological innovations that enhance the pipeline outside the classroom is where Silicon Valley and venture capital infusion lies. Inspirit AI and Strive Education, for example, are two of dozens of startups rethinking mathematics and computer science training outside the traditional classroom. This bifurcation is creating even greater inequities in society. The access and adoption of EdTech solutions by upper middle class families are happening at a much faster rate than process changes to the traditional school system. In short, the rich are getting richer with knowledge. The concept of digital citizenship needs to be taught at the K-12 level. Graduating high school seniors this past year were born in 2007, 3 years after Facebook was founded. During that time, we have seen the explosion of mobile devices, app stores, 5G, social media, autonomous vehicles, the digitization of human connection, and the ubiquity of machine learning through greater computational processing. Yet, we have not trained our students on the behaviors, pitfalls, and guidelines to harness that technology ethically, productively, effectively, and respectfully. It is analogous to giving a student from the baby boomer generation an expensive sports car on his or her 16th birthday without any driver training. There must be an acknowledgement of the jurisdiction for artificial intelligence role in the classroom. AI and machine learning are very effective tools to aid teachers as digital assistants, but at this stage, they're incapable of replacing the pedagogical rigor associated with direct teacher-student interaction. AI and machine learning can aid in the basic grading of deterministic assignments, taking attendance, and flagging performance of lags and spikes to free up educators to have greater bandwidth to transfer knowledge. However, the transference of that knowledge still needs to be human to human, as this current iteration of AI is simply sophisticated pattern matching with the accompanying inference models of the world it resides in. What I meant was without the accompanying inference models that it resides in. That is physical laws, causality, intentionality, etc. There needs to be a greater emphasis on training STEM K through 12 education teachers. While private schools in my area, for example, Los Angeles, such as Harvard Westlake, Crossroads, and others have excellent science and mathematics teachers, the public schools are severely disadvantaged. Universities, community colleges, governmental agencies, and professional engineering societies need to develop a cohesive strategy to create a pipeline of well-qualified and trained STEM teachers. The K through 12 STEM curriculum needs to be revamped in several areas. As an example, students should first be exposed to the applications of technology and inspired by them, prior to instilling the fear of mathematics and physics. And the final one is professional engineering societies, which need to work together in a more strategic and coordinated manner in providing outside the classroom training through programs that provide real-life experiences in developing engineers that are relevant to societal needs. Engineering professional societies in the United States are engaged in a wide variety of activities involving undergraduate education. However, these activities are generally not coordinated and have not been assessed in such a way that information about their procedures and outcomes can be shared. Nor have they been assessed to determine whether they're optimally configured to mesh with corresponding initiatives undertaken by industry and academia. Engineering societies work largely independently on undergraduate education, leaving open the question of how much more effective their efforts could be if they worked more collaboratively with each other as well as with academia and industry. It's important to recognize that the professional formation of engineers encompasses the formal and informal processes and value systems by which people become engineers. The key elements include introduction to the profession at any age, acquisition of deep technical and professional skills, knowledge, and abilities in both formal and informal settings and domains, development of outlooks, perspectives, and ways of thinking, knowing, and doing, development of identity as an engineer and its intersection with other identities, acculturation to the profession, its standards, and its norms. Students with these abilities have the potential to become adaptive experts, able to restructure knowledge depending on the situation. Professional societies are involved in all these elements because they have the ability to impact the field broadly, not just within a single institution or a single classroom. In summary, I think it is extremely important that we rethink our educational system based on this rapidly changing external environment that is driven by unprecedented advances in technology, and have professional societies, academia, and industry work together in creating the engineers of the 21st century. Thank you, and with that, I'll turn it over to Mark.
Hassan, thank you very much. That's a fantastic introduction for us. You covered so much ground there, and I think your call for this collaboration across all sorts of different institutions to kind of pull together to do what is needed is exactly right. So thank you very much for kicking us off so well. And now I would like to ask Jane, please, to come and share your thoughts.
Thank you, Mark. Well, good morning, good afternoon, and good evening, everyone, wherever you are. My name is Jane McMaster. I'm, as Mark said, currently Engineering Integrity Director for Babcock International, a defence and aviation multinational. I'm a former systems design engineer for BAE Systems and former Chief Engineer of Engineers Australia, one of those professional associations. I really appreciate the opportunity to talk tonight for me on this interesting and important topic, and I've really thoroughly enjoyed the comments so far from all of the speakers. Given the time constraints, and given I could talk for hours on this, as I think we all could, I'm going to limit my remarks to what I think are the three most important points about skills and education relevant to the engineering of engineering megaprojects. And I hope they kind of build on Assad's comments, which I think, as Mark said, were a wonderful introduction. So point number one is complexity. I think we've acknowledged here tonight, and we acknowledge in our day-to-day lives, that the world's becoming more complex. That means that there are more things that are difficult to understand, influence, predict, and control. And there are higher levels of uncertainty. And that applies to many, if not most, engineering mega projects, including electricity grids, large infrastructure projects, defense systems, cyber systems, airport terminals, among others. Complexity arises because of elements in a system and how they interact. And that brings me to point number 2. The field that seeks to understand elements in a system, and we've heard a lot about it tonight, of quite a few mentions, and how those elements interact, the system structure, and the behavior or outcomes that they produce, the system behavior, is called variously systems analysis, systems thinking, or systems engineering. And I believe this is a significantly undervalued skill set in the planning and delivery of engineering mega projects. Systems engineering, as many on the call today will know because you've practiced it, is concerned with how the parts in the system or the system of systems interact and how they're integrated to give the outcome that we want. Sarah spoke of the square kilometre array. We know that wind turbines and batteries and solar farms and traditional thermal power stations and transmission systems and distribution systems all need to be integrated into a system of systems to ensure the reliable, safe, secure and high quality supply of electricity. The same for defence system of systems. How all these subsystems interact and are integrated, I believe, is just as important as the subsystems themselves. And in my opinion, this aspect of engineering mega projects is routinely underestimated, which brings me to my final point, and that's around people and skills. The successful engineering of mega projects requires expertise, and a reliable pipeline of experienced engineers, including systems engineers, requires effort to ensure. And this extends well before the university years into the early school years and well beyond the university environment into the work environment. And I think it requires, above all, a strong and reciprocal relationship between senior engineers and junior engineers. I think it's the responsibility of senior engineers to ensure that they're providing opportunities to their more junior engineers to observe, to practice and to learn. But it's reciprocal. I think junior engineers also need to grasp those opportunities with both hands so that they can observe, practice and learn. And of course, it's not just engineers that are required to successfully deliver engineering mega projects. It's expertise from all professions who need to work together. That's the human capital that Donald Winter spoke about right at the beginning. And of course, it also requires a myriad of other things, such as realistic schedules and budgets. There's a wonderful book that eloquently describes successful approaches for very large projects, and it's called How Big Things Get Done. If you haven't come across it, then it's highly recommended reading. And one of the case studies they talk about is indeed Terminal 5 at Heathrow. De Villa, I'm sure you've come across it. I have come to these views after now my 32-year career, but primarily one chapter in that career. From the late 1990s to the mid-2000s, I was a systems design engineer for a NATO ship self-defense project, for which teams from 10 countries came together to develop and deliver this system. One country worked in imperial units, the others worked in metric units. Thousands of kilometres separated our 10 countries, yet the system was delivered successfully. And I put that success down to many factors, but here are my top 5, and we've heard about most of them from the other speakers already tonight. One is the importance of shared objectives and the authentic desire to collaborate and effective communication skills to support that collaboration. 2, realistic budgets and timeframes. 3, appropriate levels of expertise in the teams. 4, a heavy emphasis on systems engineering. And 5, technical governance and assurance. So in conclusion, engineering mega projects tend to exhibit characteristics of complex systems. This requires significant effort to understand all interdependencies and show how all the systems need to work together in their system of systems. Success here requires expertise. And as Don Winter noted, it takes a long time to develop expertise. We all have, I think, a responsibility to develop our future engineering workforce and to share our experiences and insight with junior engineers and to keep learning ourselves. And for the systems engineers amongst us, a renewed focus on broadening the understanding of the critical importance of systems engineering. I'll leave it there. Thank you, Mark.
Jane, that was absolutely amazing. You're totally speaking my language there on systems and systems thinking, and I literally could not agree more. I was kind of sitting here thinking, yay, everything you're saying sounds exactly right to me. It also sounds like you might have had a sneak preview of some of the stuff that the Royal Academy of Engineering has been doing on their Engineers 2030. And I know that Yarka has too. So it's a great pleasure then to welcome Yarka. It's over to you now to introduce yourself a little bit more fully and say your thoughts, please.
Thank you, Mark. And can I just double check that you can see my slides and you can see them in presentation mode?
Yes, yes to both.
Okay, apologies for this, a true academic, but I thought putting some of these messages on the slides might actually trigger some visual memories here. And over these 2 days of some fantastic presentations and some really thoughtful ideas around sort of engineering for mega projects, but actually to me, fundamentally around engineering, preparation, profession, and so on, was just absolute joy. Just very briefly to say, I'm Yarka Galassi. As Mark said, I'm a professor of chemical engineering education at Newcastle University. That is Newcastle in the UK rather than the lovely sunny one in Australia, where I would much rather be today. And if the name didn't give it away, I'm actually qualified and a Slovak biochemical engineer. So I came here after completing my education in Slovak Technical University. I'm currently a director of engineering education here at Newcastle, and therefore I'm actually responsible for all of the education of engineers at Newcastle, covering all of the disciplines that we've touched upon today, which is quite an interesting job, I have to say. But at the same time, I'm also a vice president executive of the European Federation of Chemical Engineers and also of the European Society for Biochemical Engineering Sciences, which really provides me with a good opportunity to keep an eye on the developments in terms of education and profession, at least within the European, but also global environment. And maybe as a profession, and maybe because of what Asad touched upon, it's worth mentioning that all of my career was actually dedicated in terms of research to artificial intelligence and machine learning methodologies, even before they became fashionable, but working with biopharma companies, food, specialty chemical industries. So understanding those industrial needs and why we need to make sure that our graduates are actually so conversant in those technologies. So let me just very briefly summarize a few bits that I'm taking away from these 2 days, and I will not expand on those that we've heard about more in terms of details, but it struck me that we all take the technical skills of our graduates as given, which is great. And I think the accreditation, and I'm heavily involved in accreditation with IChemE, for example, for the chemical engineers, makes sure that we are keeping at the forefront of those developments. But as we've heard, the digitalization, AI, and the need for that responsible use and application of AI and machine learning always change that context within which we are educating our engineers. We've heard a lot about systems thinking, so I'll not go there, but if I aim to achieve anything in my education here at Newcastle and anywhere I interact with engineers, it is that systems thinking and make them think their way around the problems. Yesterday, in particular, we've heard about safe and innovative designs and operation, but also a little bit about the end of life and decommissioning of the large mega projects, engineering projects. And we probably haven't spoken too much about them today, but I think there is a critical area around there that we need to prepare our engineers for. Today, in particular, we have heard a lot around the multidisciplinarity of these mega projects and how it requires enhanced ability to communicate not only across disciplinary boundaries. And it's amazing when I talk to colleagues here and when you talk thermodynamics to the mechanical engineers or to the chemical engineers or indeed civil engineers talk about fluids. We all speak our own jargon and we really do need to get out of those silos. But interestingly, today we have heard a lot around those intercultural boundaries and having to communicate across those cultural boundaries as well. And I really do think that there is a lot of work that we need to take on with our engineers in this area. I would like to also highlight maybe the decision-making accounting inherently for environmental and social impact in terms of the decisions, not just those technical and economic considerations. I know we've talked about it both yesterday and today. We've mentioned ESGs, and people do stress this in the education, but it just strikes me that the accreditation requirements demanded sustainability teaching for decades now, yet we still talk about the area of that environmental societal impact as if it was something new, and trying to get our engineers to try to consider this in everything that they do. And of course, yesterday we've heard a lot around the understanding of politics and communications with various, and I put in brackets, non-engineering, and that should not be in brackets, that's probably in particular non-engineering agencies, so that we can communicate effectively that information on the assumptions and consequences in decision-making. Frequently, that appears to be lost, and politicians will always, I guess, choose the easiest option out, and it's that 4-year cycle of anything that gets me re-elected. But raising in their consciousness that, you know, certain decisions will carry consequences is, I guess, down to us engineers. But let me come to that project that Mark kindly mentioned, Engineers 2030, which I am also involved with. And I wanted to maybe highlight a little bit about it. And you'll see at the bottom of the slide, which is why I tried to bring slides into this, there is a link to more information and really useful information around this project. And there you will find some of the background information that brought the Royal Academy of Engineering to invest energy into this project, and the understanding that there is definite need to change those educational ecosystems that we are subjecting our engineers to, at least within the UK. And at the moment, we are already completing phase 1, and there is a lovely couple of reports for you to have a look at the website, some around the literature review that led to some of the findings. But the second one, very interestingly, are the key principles that we've identified in terms of knowledge, skills, behaviors that will be needed in engineers and technicians, I hasten to say, to meet those 21st century global challenges. And we are indeed now on to phase 2, where we are trying to gain that better understanding of the systems, cultures, and policies, and more importantly, how to actually deliver change and move them to the state where they need to be to provide the skills for 21st century. So I mentioned a little bit about the project. Apologies for the quality of the figure. It was just quickly grabbed from the report, but the principles that we've identified in the report tend to group in these 3 areas: the people, planet, and prosperity. And you can see that actually when you look at the list of what we think the engineers in the future should have in terms of knowledge and those attributes and values, that is quite an impressive and I guess a bit scary list. But without this, I don't know whether we would be able to address those grand challenges that we are facing. Just very quickly to put things into international context and give me an opportunity to highlight another piece of work that the Royal Academy is undertaking together with Lloyd's Register Foundation, and it's Engineering X. And within this, I actually chair one of the boards that looks specifically at the skills for safety and how do we develop these skills right across the planet, and to understand better what that engineering safety skills landscape is. And just to quickly flag up, we have produced the report in 2019, but we're currently finalizing Global Engineering Capability Report 2024, which should be out later on in the year. And that to me is a really important review of various critical areas for engineering profession, answering 3 key questions, and I'll let you read those questions in there rather than get into the detail of it. But to me, for us engineers to understand that whatever we do has significant impact on the society around us is something that is critical to develop in our graduates as we going forward. And with that, I guess I'll leave it to our last presenter and we'll then try to answer some of your questions if I can manage to stop sharing as well. There we go.
Jelka, thank you very much. It feels like a pattern is starting to emerge, isn't it? So I think it's going to be very interesting when we've heard from Kevin to see how we bring all of these threads together. But I'm already spotting some patterns. So Jelka, thank you very much for that and for introducing those important initiatives. And Kevin, if we could ask you to turn your video on, introduce yourself and your opening thoughts. Thank you.
Yeah, thanks, Mark, and thanks everybody for what you've presented so far. I thought I'd take a little bit of a different approach. I'm going to really focus on talking about challenges as opposed to what we're going to do. And I've had the privilege over my career of working on a number of mega port projects. I'm a coastal and marine engineer. For about 40 years, I've been working in that field, but I've also had a long career as an educator, from a professor to a head of a school. I've been a vice president research and now a president and vice chancellor at the University of Victoria. So I've been kind of the full cycle from teaching and research to managing, and now doing government negotiations, which are creating lots of problems for us in producing the right engineers for mega projects. I'll talk a little bit about that later on. I know Eddie talked a little bit earlier about the Canadian Academy of Engineering mega project workshop, which had a great scope and breadth, where academia came together with industry and government. And I'll riff off that a little bit. But just to acknowledge that the cornerstone of any successful mega project is really that skilled and robust workforce, particularly in the field of engineering. But of course, we do have to work with others. And in Canada, we're really facing a challenge to develop, attract, and retain engineers and technical professionals. The current workforce demographics are revealing that we've got a really looming shortage of experienced personnel. Exacerbated by factors such as retirements, there's skills mismatches, and really, I think for universities, insufficient recruitment efforts to get the right people into our programs. And so we're really focusing on trying to generate multifaceted approaches to workforce development. That's not just your traditional student, the ones that come out of high school in particular, but how do we tap into the mature students that are out there that are capable of going to university but haven't had the opportunity? And what are we doing around upskilling the existing professionals into areas that really support mega projects? And I think we tend to be very risk averse at universities. We're not overly innovative. And so how can we actually create a lot of structures to become more innovative in the way that we're teaching students, the way we're mentoring students, looking at using retiring engineers, for example, to impart their knowledge on younger professionals. I think for me also, one of the tougher pieces is convincing governments to invest into education and training programs in partnerships with universities and colleges. And so in theory, it sounds easy to create that workforce, but I was going to just highlight what I think are some of the major significant challenges. And I think let's start with the attraction of students into the classic fields that really support mega projects, mechanical, civil, electrical systems. There's a huge interest right now in high tech, and I'm sitting this morning in Silicon Valley. I'm down here meeting a number of our alumni, about 20 alumni we met with last night. They've been highly successful in tech careers down here. They're not interested in mega projects. They're interested in making a lot of money, and they're kind of the role models for a lot of the students that we see coming through the system. The government itself in Canada, government in British Columbia, which is our province, which funds education, is interested in computer science. We've had a funding of 2,000 new seats in computer science over the past 2 years that I've been at the University of Victoria, but no funding in the traditional programs, no additional seats. I think we've also got issues around accreditation. We all have our accreditation systems in each country. I know they talk to each other, but do they actually work together and make sure that accreditation is seamless across the globe? There's some work we could be doing about there. I do know that thinking about new programs that we might need to support mega projects, to look at global markets, and to look at the new types of students that we're going to get into our system if we start looking at mature systems. Is the accreditation systems ready for that? Are we agile enough as a sector, as engineers, to actually approve and look at new ways of teaching and new ways of learning? The length of programs that we have is often questionable. We have a 4-year program in Canada for engineering, a 5-year. If you look at a co-op, that sometimes can be problematic. And so what are we doing in terms of the frameworks for building programs that are of shorter duration to get more people trained in a quicker way? One of the passions I have is supporting accessible education. So by that, I mean, getting people into the system that are not your typical high school leavers. And so in Canada, we don't deal with mature students very well. If you've not finished high school or you've gone out to work, you've decided you want to come back in your mid-30s with a family in tow, we make people go get their high school degree. We don't create pathway programs into engineering. And so we're missing out on a large piece of the population that could be absolutely fantastic engineers in this field. I also feel that work integrated learning and co-op are really critical to developing engineers that are going to be valuable for working on things like mega projects. And so what are we doing as a university sector, again, to increase the opportunity of cooperative education, where our students go off and get some experience working during their education, or in fact, just short-term stints as work integrated learning, getting more professionals into our classrooms. And the last thing we're really trying to focus on is looking at upskilling and reskilling the existing workforce, because I think that's going to be a critical piece for engineering and in the future. And so, what are universities doing? How are they working with their learned societies, their accreditation systems, to look at micro-credentials, for example, and how we could offer micro-credentials as part of continuing education, but really changing the shape of somebody's career. I think the last thing I'll talk about is really technology integration. So we all know we're in an era really marked by rapid technology advancements. So integrating innovative technologies is really critical for enhancing the efficiency, safety, and sustainability of mega projects. But at the same time, it's not only about engineering design, construction processes, and project management, but it's about our engineering education. Are we ready to really start looking at digitization, automation, artificial intelligence in the delivery of education? And so at the core, it's really about how and where are we going to teach these critical pieces around technology integration. I think the other piece where universities and engineering departments can play a big role is investing in research and development. That's really crucial for driving that technological innovation in the engineering sector. And so things like establishing centers of excellence focused on mega projects and fostering collaboration between academia, industry, and government. And I know we say that every single meeting we get together at. We said that 40 years ago when I was a young professor. We have to have more integration between academia, industry, and government. And I can't understand why it's so hard to accomplish, but it's something we all have to sort of roll up our sleeves and pitch in and make it work finally for this time. And so I'll finish up this by saying I think workforce development, technology integration, and things like supply chain management are all these interconnected pillars that underpin the success of mega projects in Canada and globally. And I think universities have a huge role in talent development, in embracing innovation, and really embracing technology in the delivery and perhaps the speeding up of engineering education. So thanks, Mark.
Kevin, thank you very much for rounding us off on some, I think, really enlightening opening thoughts to get us going. And I would just ask, as everyone gets pinned and so we can all see each other on the screen, I think what Kevin was doing there so nicely for us was summarizing the challenges. And I'm just wondering whether some other people on the panel would like to kind of add to that pot Yeah, Kevin has definitely started it off well for us, but let's just kind of consider, what are these challenges that we're facing, and then maybe we can move the conversation into what the solutions are and what the academies can do about it. So to the other members of the panel, would you like to maybe just chip in to kind of build on what Kevin was saying around what you see maybe as the key challenges? So Asad, coming to you, what is it that we're actually trying to solve here? I think you're on mute.
I think what we're trying to address is a very complex issue. Our needs are not absolutely defined. They're adapting because technology is driving us in a manner where what we think is needed today is not necessarily the same thing that is needed tomorrow. And so it's very important, one of the things that Kevin said, take accreditation, for example. Just talking to each other with the accreditation boards is fine. But unless there is a focused and a determined effort to make sure that we are working to address the needs of the future workforce, these will be idle curiosities. And I've sat in enough meetings to know that unless there is a very specific funded effort with specific benchmarks, these will be nice get-togethers that will absolutely result in nothing. And so it's really important that we understand that. Second thing that we need to understand is that as technology changes, our people within our organizations all have got to be in constant mode of learning. Like Peter Senge of MIT said many years ago when I was there, more than 30 years ago, is the learning organization and the learning individual. People who are knowledgeable were very highly respected at one time. But that is because the external environment remained more or less constant or was moving very slowly. Today, there is a very rapid move in the external environment. So unless the workforce is constantly being educated, the knowledgeable people will end up as historians and not as actually constructive workers. So from the top of the management all the way down in industries, in professional societies, and in academia, there has to be an understanding that not only is this the important thing to do, but for the United States, for example, or any country to maintain their leadership role, they have to lead this path and make sure that this interaction takes place and there are specific benchmarks in terms of what we want to accomplish.
Yeah, that sounds very important, doesn't it? And you're, I think, pointing to this issue of being able to cope with constant change. I mean, it does feel that we should be able to do something to make ourselves more able to do that. And I'm just thinking to the Engineers 2030 paper, and Yarka, I'll come to you on this, with the whole idea around phase one, focusing on the kind of the knowledge and the skills and the behaviors which are required, which seems to be something that is needed almost irrespective of the change. We need to be considering those. So I don't know if you want to just kind of pick up on that point, that in this context of things changing, what can we be sure of?
Yes, Mark, I fully agree with, sentiments expressed by everybody, but Kevin and Asad in particular now. The rate of change is much greater than what it was when we studied. And interestingly, we are still stuck, and this is not this is a natural human behavior. We were exposed to some level of education, and the natural human behavior is we go with what we know, but that is not going to be good enough in the future because of those changes. And critically, in the past, because the information wasn't as readily available as it is now, a lot of what we were learning was more or less those fundamental principles and some of that knowledge that currently is available literally at the click of the mouse, but you have to be careful of what you believe in. So getting the future education or future engineers to understand that actually that criticality of what Asad just said, you have to keep learning. So it's actually the frame of mind that's more important. Yes, absolutely. You have to know your first principles. And luckily enough for us, those fundamentals do not change. You know, the conservation laws still apply and hopefully will apply for quite some time. So yes, we need to understand them. We need to be able to apply them in new context. And that then requires the constant drive to learn, that curiosity of the mind. But interestingly, as an institution, I always used to say to my colleagues, there is a difference between training engineers and between educating them. And for the engineers that are leaving us now, we really need to educate them to make sure that they learn and they learn to think. But interestingly enough, I think also for the practicing engineers, there is that critical need, I think Kevin touched upon, of upskilling and reskilling. When you're really saying, well, okay, the technology has moved on so far that there is time now to just quickly catch up with, this is what is already happening. This is how you can utilize it in your profession. And that comes closer to training. But again, there is a role for universities to actually play that role as well. It's just we need to be careful about not trying to do that with the future generations of engineers and just train them in this little pet or that little pet. I said, I hope you didn't mean when you were talking about the accreditations and the specific standards to be too prescriptive, because in some way, that worries me with some of the accreditation documents that I see around the world. We've done quite a bit of work around, you know, the accreditation requirements, and I work in a system where Engineering Council is relatively broad speaking, and they define their AHEP intended learning outcomes very broadly so that you can actually adapt as the technology changes. But I have seen examples where it's very specific. You shall know this and you shall know that. But it then doesn't allow that space for agility and adjustment to new developments. So in 2030 or Engineers 2030, I think what we are trying to emphasize is more that sort of, yes, indeed, fundamentally, you need to know the basics, but you have to have that frame of mind to keep learning. And
Yarka, I was actually trying to say exactly the opposite.
Fantastic.
What I'm trying to say is that each one has their prescriptive formulas.
Okay.
There is, if that's all you want to do is stick to the prescriptive formulas, there's no need to have collaboration. The reason for the collaboration is to have diversity of ideas. And I think
Absolutely.
the best way I can explain it is, I was very fascinated by the report that the National Academy put out called The Engineer of 2020 and Educating the Engineer of 2020. And it was a dramatic last paragraph, which meant a lot of things. It said, the engineer of 21st century, he or she, I hope I say this right, he or she will aspire to have the ingenuity of Lillian Gilbreth, the problem-solving capabilities of Gordon Moore, the scientific insight of Albert Einstein, the creativity of Pablo Picasso, the determination of the Wright brothers, the leadership abilities of Bill Gates, the conscience of Eleanor Roosevelt, the vision of Martin Luther King, and the wonder and curiosity of our grandchildren. Now, what they were actually trying to say is that the engineers of the next century, they have to have depth, they have to have breadth, which is the T graduate, they have to be socially conscious, they have to be ethically aware, they can't just be supervisors and managers, they have to be creative, they have to learn how to take risks, they have to be imaginative, and they have to be inspirational. So what I'm saying is that none of these aspects, besides the depth aspect or the breadth for that matter, is what the accreditation boards cover.
So let's move on then to the solutions. So we covered what the challenges are, and I think that's actually a really useful build. But in hearing what you just said there, Asad, I can't help feeling that sounds like individual engineers, like individual spots of light who are going to have all this capability. But what about engineering? How do we bring it together into something that actually helps the world? And what I think I was hearing Jane saying, in introducing brilliantly this stuff around the systems thinking, is integrative. It's how do things come together in something that works. So I wonder, Jane, if there's something that you might like to add in this systems thinking space about how do you bring skills together in a way that is effective.
Yeah, thanks, Mark. I'll certainly have a go at answering that. But first, Assad, what an incredible list. And doesn't that just illustrate how much an engineer is, if not expected to learn, then at least has available for their learning? It's an awfully long list. There are huge expectations, if not for individual engineers, and certainly for engineering teams. I think engineering teams, if we're talking about bringing engineers together to work on these engineering mega projects, we're facing 4 main challenges. There are probably others, but these are the 4 that have come to me during the conversation. One is the number of engineers. I know certainly in Australia, we produce the 2nd lowest number of engineering graduates as a proportion of all graduates in the OECD at just 8%. It really is a challenge. There are just not enough engineers for all the engineering work available, and I'm sure that is similar in other countries. But it's not just the number of engineers, it's about the skills. That's what we've started talking about now. And there's only 24 hours in each day, there's only 365 days in each year, and we have to sleep some of it and do other things. As Assad's just pointed to, the enormous range of things that engineers could be not only learning, but mastering, being able to practice those things. And I think for me, the importance of skills and knowledge all converges on an engineer's ability to form sound engineering judgments. That's what we need engineers to be able to do individually and collectively in teams, to be able to form sound engineering judgments. Because more often than not, the implications of an engineer's work have serious safety and health implications for our communities and for the public and for workers. It also has economic consequences in terms of how our systems perform. And so it's really important that engineers can form sound engineering judgments. And often that's not easy because of all the uncertainties that we've been talking about. So you need that unique combination of deep subject matter knowledge, the breadth that Assad just was talking about, and being able to bring that all together to be able to form sound engineering judgments. And I think the 4th and final challenge is more for our profession, but also we experience it on an individual basis, and maybe everyone listening and maybe the other panelists would like to comment. I think our profession, someone touched on this earlier tonight, but only briefly, our profession needs to explore how we can be more influential. More and more we're all working collaboratively on multidisciplinary teams, and often engineers speak in engineering language, we use engineering terms, even the ideas, which are quite common and natural to us, can sometimes come across as quite foreign to others. And so the more systems, technology we have in the world, it influences almost every aspect of our daily lives now. I think the more impetus there is for engineers to be influential and to have the engineering and technical perspective heard in policy and decision making. I don't know what the answer to that challenge is, but I certainly think it's something that we should be putting our collective attention towards.
Yeah, thank you, Jane. I think that's really thoughtful. Those kind of 4 areas of challenge, I think, totally resonate with me. And certainly something which I feel is that it isn't going to be enough just to focus on individual engineer skills, but rather collective engineering capability, because no one engineer can know everything, but together we can do amazing things. And not just engineers, because as you just indicated, we've got to plug into others who do other stuff. And they need to understand what we can bring, we need to understand what they bring, and we've got to somehow integrate it. So Kevin, something which I'd be really interested in, now that we've done really quite a good exploration of what the challenges are, let's try and kind of turn our attention to what we can actually do to solve some of the challenges. Because Jane was just pointing out to some real skills shortage just now. In the UK, apparently, it's something like between 35 and 50,000 engineers and technicians every year, that sounds like a problem. So let's see, what are the solutions? What can we do? Can you bring some solutions to the party?
Yeah, I'll try, Mark, with a couple. And I think, for me, in being in Canada, I should say I spent half my academic career in Australia, half in Canada. Both systems require government funding for these programs, and we're not private systems in Canada or Australia. They're public universities, and so half of the fee is paid by the government. Getting the government excited about supporting the mega projects that the countries need is something that's critical, because, as I mentioned earlier, 2,000 new seats of computer science. Well, that's fantastic, but it's not going to help tremendously with the major power projects that Canada wants to undertake as part of its commitments to net zero. So I think lobbying government, I guess, getting the proper funding. The second piece, that I really admired about my time in Australia, my recent stint was at Newcastle, Jarka, but the University of Newcastle with the sun and the sand. I went there in 2010 to be the Deputy Vice Chancellor in charge of research and innovation, coming from a Canadian university. And I was amazed at the pathway programs that were established at Newcastle. My university, Newcastle, was 55,000 students. 60% of those students were mature students, and they were considered to be out of the system for more than 5 years, many of them without high school degrees. But the government paid for and supported pathway programs, including engineering. And so you could be in your 30s with a couple of kids, and you could decide you wanted to go back and work as an engineer because you were smart, but you didn't have that opportunity. And the mechanism was there for it. And so if we can't get enough school leavers to go into engineering, where are the programs, the pathway programs, to get people who are actually, quite frankly, really keen on studying? They work much harder. And the Australian system has shown that the success rate of students that go through pathways in engineering is much better than it is the high school leavers. They graduate with higher marks. More of them go on to graduate degrees, and the retention is much better. And so I think there's a couple of solutions. The third one is, it's beyond me. It's getting accreditation systems to be agile as well. And I know we have to have standards, and we base our standards on years and years of engineering education, but maybe it's time to be a little innovative in the way that we look at and accredit programs.
Thank you, Kevin. And time is doing what it always does. It's always against us. But I think there probably is time for us to go round. And in this same kind of theme of trying to get some real answers, I think maybe we can just have like a closing thought. If you ruled the world for a day, and you could have your wish as to what could be solved, what would it be? In this area of skills and capabilities. So we're going to buzz around pretty quickly. So if you can just kind of be succinct, but it'd be really good to hear from all of the panel. What would the one thing be that would make the big difference? So I'm going to go in kind of a random order and go to Jarka first.
Thanks, Mark. Maybe I'll just say how subversive we were in those Engineers 2030 discussions. And we actually said, dismantle the education system as it is now. In the UK, having grown up in Slovakia, I can absolutely see why. In the UK, we channel people too soon into, you can either do humanities or you do numerical sciences. But Kevin, it goes against all that, bringing the capabilities together. So let's talk. And at Newcastle, we teach our chemical and electrical and civil and mechanical and marine engineers together in the first year, because they need to talk to each other. So break down silos.
Break down silos, reinvent the education system. So Jane, very briefly, please, what would you do?
Very brief. I'm going to sneak in two, Mark. One, you won't be surprised. If I had a magic wand, I'd give everyone systems thinking skills. I spent 6 years teaching non-engineers simple causal loop diagramming techniques so that they could understand multiple causality and feedback loops. And I saw people's eyes light up, and it was really powerful. So I'm convinced that if people are introduced to system thinking concepts earlier, we'd all do better work. And the second quick one is, I think we need to do a better job at inspiring our young people to understand what engineering is and to consider further study and a career in engineering. If we don't do that, we're not going to get the pipeline of people that we need.
Okay, thank you, Jane. So now, very, very briefly, please, Kevin, and then the last word will go to Assad.
Yeah, well, I've said quite a bit in terms of solutions already. For me, work integrated learning, a cooperative program should be mandatory in engineering, and that would help bridge this divide between academia, industry, training, and education. And I think the more students get exposed to actual engineering during their degrees, not just from professors at universities, it's a great thing.
Thank you. Assad. Again, I think it's mute.
I would say that the most important thing I would do is make an effort to have a culture of continuous improvement and understanding in engineering based on the changing environment. And that should be a culture at the management level that permeates down to create this overall competency. And while systems engineering, I think, is extremely important, to emphasize the fact that it's not just block diagrams on top of block diagrams. Systems engineering has to have a deep understanding of the hardware that is involved, and very few people talk about that. All they talk about is software and block diagrams, which I think is fine, but unless you have a deep understanding of the hardware, it is, take a very large program, for example, you know, when you're sending a mission to Mars or somewhere, software is important, systems thinking is very important. However, it's the hardware that actually goes there.
Thank you very much. So you can have everything you wished for there because it all sounds good. So we're going to break the silos. We're going to teach systems thinking. We're going to inspire young people, do integrated learning, and make an effort to have this culture based on changing environment. We've got it. Let's do it. So panel, thank you very much. You were absolutely brilliant. And with that, I'll like to hand back.
Well, thank you very much indeed, Mark, and the whole of the Block 4 panel. What an interesting discussion that was. My name is Hayatun Silem, and I'm the CEO of the UK's Royal Academy of Engineering, and I'm honoured to be closing out both today's discussion and this Ideas Forum on Megaprojects on behalf of the National Academies of Engineering of Australia, Canada, the US, and the UK. Well, we have travelled right around the world and even into space over the course of this forum. And it would take me far longer than my allocated time to do justice to the wealth of perspectives that we've heard. So I'm going to simply share a few reflections. Yesterday, our academies looked at the technical, social, economic, and policy issues impacting the delivery of individual megaprojects, which already seemed like a pretty bold agenda. But today we took an even broader perspective and examined the shaping environment in which engineering megaprojects are delivered. Donald Winter gave us a powerful provocation, which addressed the challenges of securing the supply chains, power supply, IP, and human capital needed to underpin successful projects in a global environment made unstable by geopolitical tensions and the existential threat of climate change. Don reminded us that tackling this requires us to take a long-term view and to ensure that we align timing, investment, and resource allocation. And Don also highlighted the importance of increased collaboration and better communication between industry, academia, and government, and also between countries which share the same values. And these are areas where I would suggest National Academies of Engineering can also contribute. Broadening out into the wider Block 3 presentations and discussion, some of those key themes were echoed and amplified. We heard that collaboration at multiple scales, cross-sectoral, cross-country, cross-profession collaboration is a really essential component of delivering mega projects, but it is also a significant source of complexity. And some of the approaches suggested by our speakers to maximize the upside of collaboration and manage that complexity included clear and common goals to create alignment supported by charters or frameworks that bring clarity on roles and behaviours, investing in identifying the right partners at the outset of the project, and then in building trust over the project lifetime. Having a laser-like focus on the intended outcomes the project is seeking to realise, and recognising that this requires respectful and sustained engagement with end users and with those who will be impacted by projects. And of course, last but not least, we heard that systems engineering and systems approaches, which are so core to our engineering habits of mind, are essential tools in the mega project toolkit. Over the course of these 2 days, our speakers have done a great job of distilling many thousands of person years of experience into salient lessons and insights. So having built up this knowledge, how can we share these insights with those starting out in their careers, as well as learning from their different perspectives, noting that diversity of thought is a key contributor to creativity and to resilience? Well, that brings us on to Block 4, where we heard some exciting and creative ideas about how advanced project management and systems thinking can be encoded in the formation of the next generation of engineers. We heard about the imperatives created by rapid technological change, from embedding digital citizenship to revisiting the fundamentals of how and what we teach. We heard about the importance of intergenerational learning and facilitating conversions into and upskilling within engineering at all career stages. And we heard about the need for greater collaboration across professional engineering organisations, which led into discussion of our own Academy's Engineers 2030 initiative, which is seeking to convene UK stakeholders around a shared understanding of what it means to be an engineer in the 21st century, with the objective of catalysing a sea change in engineering education and professional formation, so we are a profession fit for the future. And I know that there are other similar and important initiatives underway across all 4 countries represented here today. Our Academy's founding senior fellow, the late Prince Philip, had a very pithy way of highlighting the importance of engineers. He famously said, "Everything that wasn't invented by God was invented by an engineer." Well, however we choose to express it, it is certainly true that there is no part of modern life that has not been touched by engineering. As the complexity of our engineered world grows, as societal need grows, as technological capability grows, as our ambition grows, so does the importance of ensuring that our engineering community is equipped to fulfill our professional obligations to society. As we've heard over these 2 days, engineers will, in collaboration with other professions, need to design, build, manage, and maintain the essential infrastructure and systems that will promote inclusive economic growth, strengthen democracy, and protect us from the threat of climate change. And in doing so, as noted by Sir John Armitt, we need always to be ready to address the why, the what, and the how of megaprojects, the megaprojects which will underpin all of these societal outcomes. And I'm sure that our academies will be reflecting further on how we can support this. So in closing, I would like to thank all our speakers and moderators for their excellent contributions, all the staff who worked so hard to make this event happen, and to all of you for listening and engaging with us. The recordings will be posted on NAE's social channels, and we would welcome your engagement with the ideas that we've shared over this forum. We look forward to hearing your thoughts and to building on this collaboration. Thank you very much.